Example number 2. For the region S in example 1, show that the sum of the areas of the upper approximating rectangles approaches 1/3. That is the limit of R of n when n approaches to infinity equal to 1/3. So R of n is the sum of the rectangle when we are using the right endpoint. So if we just look at this first rectangle, so we have the width is 1/n and the length is, you plug in y, so you get 1/n squared. So that is the first one, the area of the first box. Now let's look at the second box. The width is still 1/n and the second part is 2/n. When you plug into the y to find the height, it will be 2/n squared. So we continue to do that. For the last one, the width is 1/n and n/n, which is 1 square, which is the last rectangle. Then we will factor out the common factor, which is 1/n and 1/n squared. So we got 1 square plus 2 square and ... plus n square. We have the formula for this. So this is n times n plus 1 times 2n plus 1/6. And then we simplify this expression to get the answer is n plus 1, 2n plus 1/6n squared. Now we go back to the original problem. We want to find the limit of R of n when n approaches to infinity. And we just calculate the R of n above. Then we plug it in. We use some algebra to separate the n square in the bottom, become n and n. And then we use algebra again to divide. Then we can see that when n approaches to infinity, this part is 0, this is 0. So we will have 1 times 2 from here. And 1 times 2 is 2 times 1/6 in the front. And we can show that the limit for the sum of the rectangle that we are using from the right endpoint is equal to 1/3. Similarly, we can able to show that the left endpoint is also 1/3. Then we can conclude that combine the example number 2 and this one, so you can show that the area in the curve y equal to x squared between 0 and 1, it is 1/3, which is this area that I shaded.